Okay, so this is the last CO that we have to cover, and the statement of this CO is appraise graph oblique tree structures and basic operations on them. So we have to cover either graphs or the trees in this course. So I am going with this graph, okay? So because you have the tree information in the data structures. In the data structures, I think maybe you have some information regarding graphs, but not in detail, but the tree data structure you will study in detail in that course. And hopefully you already have studied data structure or not. So if you have already studied that data structure, then it means that you have the information of that tree. So so we have to go with the graph or the tree. So I am going with the graphs, not with the tree. So just a minute. So this is the first section of the chapter 10 from your textbook. And the first section is graphs and graph models. So first we will see some theoretical stuff about so that we can get the understanding of different terms which are available in graphs. So first we have the definition. What is a graph? So we can represent graph with G symbol that will have the set of vertices and the set of edges. V is for set of vertices, which means set of nodes or set of terminals, you can say. And E is a set of edges. So this V would be a non-empty set, non-empty. Yes, of course, non-empty, because if you will have some nodes or vertices in the graph, then you will have some shape of the graph. If that set is empty, it means that there is no node and there is no graph. So a graph, now this is the definition of the graph, that the graph would be G is equal to VE, that would consist of V, and this V would be a non-empty set of vertices or nodes. And it will contain E. E is what? E is a set of edges. So if you have a edge in the graph like that, then that edge will have what it is saying. Each edge has either one or two vertices associated with it. If this is a complete edge, then there are at least two vertices or nodes are needed, which will be associated or connected with that edge. There, in some situations, there would be one node that is also a graph, but here you don't have the edge. Okay. So anyhow, so if you have an edge, each edge will connect with one or two vertices. And why one? Because this, according to this definition, okay, when you have only one node. And it can be a loop on that node, like that. It can be a loop. And now you have only one edge. So anyhow, each edge has either one or two vertices or nodes associated or connected with it. So these nodes, you can also call them endpoints of that edge. So this is a different term. Endpoints of that edge. You are seeing the word endpoints for the vertices, but now you are saying with respect to edge, not with respect to vertices. So that's why you are saying these are the endpoints of that edge. So now, anyhow, so these are the different terms that will be used, that you will see in your textbook. So it is so then it is necessary to understand those terms, because English is not our language, but we have to understand that text. So, and then, so you can also say that edge is said to connect to its endpoint. So if this is an edge, then it is connected with these two endpoints. And now we will see what is infinite graph. A graph that will have the infinite set of vertices, that can also be called infinite graph, or a graph that will have infinite set of edges. In a graph, you have only two things. And if any one of these two things is infinite, you can call that graph an infinite graph, nothing else. And then finite graph, yes, that is the opposite of that, infinite. In the finite graph, you have the finite number of vertices or the finite number of edges. There is no infinity in that graph. And now we are going to see the definition for the simple graph. What is simple graph? So, what is simple graph? A graph, by the way, a graph in which you don't have the multiple edges are the loops. So that is called simple graph. That is also a definition. But here it is a more simple definition, that a graph in which each edge connects to two different vertices. So you can imagine a graph and you can imagine its vertices. And if each edge of that graph is connecting two different, always connecting two different vertices, this may be the simple graph. Let's see. Yes, it is a simple graph. For example, here you have these nodes, and this edge is connecting this one and that one. And this edge is connecting this one and that one. Now the nodes are different. This edge is connecting this one and that one. Nodes are now different. So this edge and that edges. And similarly, so this is not only the definition, there is the second part of the definition. A graph in which each edge connects two different vertices always, and no two edges connects the same pair of vertices. For example, if I have an edge like that, so now this edge is connecting this one, San Francisco and Denver, and this edge is also connecting the same, San Francisco and Denver. So this is covering this second portion. So a graph in which you don't have the multiple paths, simply, if a graph in which you don't have the multiple paths are the loops, loop is this thing. This is the definition which I told you in the beginning. But this definition is okay, written in a complicated way, okay. So a graph which will have no multiple paths or loops would be called simple graph. Or a graph in which each edge will always connect two different vertices, and no two edges will connect the same pair of vertices like that. That would be called simple graph. Multiple edges. This is multiple edges. If you have two nodes, vertices, so one edge is already going there, and if you have the same edge going from the initial node to the terminal node, from first node to second node, if you have two paths, so that is what multiple edges. That is what multiple. I am calling this edge also a path. That is also a term used in these graphs. And if some graph has the multiple edges, then that graph will be called multigraphs. If some graph will have these multiple edges in it, either one or two or many, that graph would be called multigraph, sorry, multigraphs. I think it will be shown here. Yes, in this figure too. You can see here that this is the node Los Angeles and Denver, and you have the multiple paths between them. This is not a loop. So here we don't have the direction. So it is undirected graph. One thing, it is undirected graph. We don't have the direction. So this path means that I can go from this Los Angeles to Denver. I can go from this Los Angeles to Denver. This is another edge. Or you can consider it in opposite direction. No issue. So this is a multigraph. Then what is loop? Loop, you know that. If the starting and ending of an edge is the same, that is called loop. I am giving my own definition to you, not reading from here. Okay. If the starting and ending of an edge is the one node, then that is called loop. For example, here it is starting from here. Here we don't have the direction, so that's why it is a little bit ambiguous, but don't worry. It is starting from here and ending here. So that is a loop. That is a edge, but that edge is called loop. And you have many loops in this graph. And now pseudograph. So a graph that will have the loops and also sometimes multiple edges. So you can finally say that a graph that will have the loops or the multiple edges, that graph can be called as pseudograph. For example, I can call this a pseudograph. I can call this a pseudograph also. Yeah, so that's why it's possibly a word is there. If you have any one of these two things, if you have any one option is there, so that is pseudograph. If both are there, that's good. So now we have basically we are going to see that there are the two main categories of graphs. One is undirected, another is directed. And no doubt, undirected means you don't have the direction here like that. Here in this graph, you don't have the direction. Here in this graph, you don't have the direction on the edge in the form of arrow. You don't have the direction. So that is called undirected. And if you have that direction, that would be called a directed. For example, now the directed graph, the other name for directed graph is, this is the short version, digraph, means directed graph. So that graph will have again the set of vertices and the set of edges. And this V would be non-empty set of vertices. And this E would be set of edges, but now directed edges. Okay, now directed edges. You can also say them arcs that you already studied in mathematics. So now in the directed graph, you will have the directed edges, which means edges with direction. And you can represent each edge with a pair like that, with a pair U comma V, where U is a vertex, V is also a vertex. U and V are nodes. And what it is saying that that edge is starting from here, this U node, and it is ending at this V node. So U is the starting vertex or node of that edge, and V is the end point of that vertex. Now, what is simple directed graph? So a directed graph with no loops and no multiple edges. So now that we have that definition. So a directed graph. What is simple directed graph? So it is that, so direction is there. So that's why we are starting with this one, a directed one, a directed graph with no loops and no multiple paths or edges. That would be called simple directed graph. Let's see, this is simple directed graph or whatever. We have the direction here mentioned on these edges. So it means that this is directed. And do we have the multiple edges here? If it is, then this is not. This is not the example of this one. Maybe it is figure 5 is for something next. So for example, here, from this San Francisco and from this Denver, maybe just look at it here. Maybe this is the example of this one, this definition too. Denver and no, I'm looking at here on this one. This Los Angeles and Denver, the direction is there, and the direction is there. Now direction matters. So now this is not parallel paths, okay? These are not multiple paths, you can say. The direction is different, okay? Now the direction is different. So this is a directed graph, let's see. And we don't have any loop over it, that is clear. Now we will see that is there any multiple paths here? So this is only one edge, that is okay. Here we have two. One is directed from Los Angeles to Denver. Other is from Denver to Los Angeles. So these are not called multiple edges, okay? These are different edges in different directions. Okay, here the direction is different. Here the direction is different. Okay, okay. So on all the edges, the direction is different. So you don't have multiple paths in this graph, and also you don't have the loops in it. So that's why this is an example of simple directed graph. Simple directed graph. Because this graph has not any, does not have any loop or the multiple edges. And then, okay, multiple directed edges. So now we are going to see directed multigraph. Simple directed graph is over. Directed multigraph, yes, it is clear that it would be the directed graph, and then it would have multiple paths. If that graph have multiple paths, then we can call them the directed multigraphs. And what is its distinction? How can we identify? If that graph will have multiple directed edges. For example, this one. From San Francisco to Denver, we have one edge going from here in this direction, this one. And also this edge is going in the same direction. So now these are the multiple directed edges. So now this is an example of multiple directed edges. Which means that you have the edges, multiple edges of same direction between two nodes. So that is the multiple directed edges. And this is now the example of what? Directed multigraphs, not only multigraphs, okay? And we can see the, for example, the direction here also, the same direction. So multiple directed edges in this graph. And what is the mixed graph? A graph that will have the directed and undirected edges. A graph that will have the directed and undirected edges, that would be called mixed graph. Okay, moving forward. Graph models. Now you will see different graphs which you can draw for different purposes. For example, and these are called graph models, okay? And these are called graph models. For example, here in this example 1, you have a graph for friendship or acquaintanceship. It's the same thing. Friendship is level high, acquaintanceship is just starting friendship, you can say. If some person know other person, that is acquaintanceship. So this would be the graph of your Facebook, okay? Facebook friends. Facebook friends. For example, here, I don't know. So there are the different names of the persons are mentioned. Jan, Eduardo, Paula, Todd, Kamlesh. These are the different. For example, if this is a graph from your account, Facebook account, then these are your friends. Then these are friends are the friends of friends. For example, Jan or John is a friend of Paula, and that Paula is a friend of Eduardo, and that Paula is also a friend of Todd, and that John is also a friend of Leela, and so on. So this is the simple graph, nothing else. So this is one model. So this is called graph model, but this model is saying this is the friendship graph model, or it is representing acquaintanceship. And if there is a node like Jan and Paula, if they are friends, is there any need to represent another edge from here to show that they have two kinds of friendship? So therefore, no multiple edges and no loops are needed. Loops, Jan to Jan, you are friend of your own. So that is not reasonable. Okay. So multiple edges and loops are not reasonable here. And now example 2. This is the influence graph, which means maybe in my circle, how, or for example, maybe in this class, how each person has influence over other person. How each person has influence over other person. I don't know the Arabic word for asr, maybe. I don't know asr is the Arabic word or not. Aleph, say, re. But say is something you pronounce differently, so that's why you will not understand. Atar maybe. That is the smell. Anyhow. So here we have the influence graph. And if it is an influence graph, then you can understand that one person have influence over other person. So direction is there. Sometime it can happen that both of these persons can have the influence over each other. If that condition is given, then you can represent multiple edges, otherwise not. But here it is a simple one, so that's why no multiple edges. If no multiple edges, it means that if Brian has the influence over this Linda, then Linda don't have any influence over this Brian. But it can happen if the condition is given. But here the condition is not given there. So that's why no multiple edges here. And no loops because Brian has influence over it, so that is not reasonable. And similarly, Deborah is a influence over Linda. Deborah is a influence over Fred. And you can say anything here. So this is an influence graph. Influence like power, I have power. Yeah, you can say you have some kind of authority. I don't know. That is the power or the friendship or whatever it is. You have some kind of authority to affect on the decisions of the other persons. What? Sulta? Sulta. Okay, okay. Okay. So this is example 2, okay? This about influence graph. And then example 4, which is so this is also a model. And then this example 4 is about, it is a call graph. It has 2 parts. First is the diagram, which is the A. It is calls from X to Y, calls from one number to another number Y. And then we have another graph B, connection between X and Y. The other graph is just only showing that how these two numbers have the connection at some point. They connect with each other, not any other information. But this graph is which number X is calling to which number, because the direction is there. So for example, this number, and that number, we have the communication between them. And here, this edge means that that this number is calling to that number from this direction. From this direction, direction is downward. So this number ending with 1, 2, 3, 4 is calling 9876. And similarly, from this direction, which is that one, this 9876 is calling 1, 2, 3, 4. And we have the same ideas also discussed here with or among different numbers. So from this graph, you can have the understanding that when one number is calling to other number, and how many, then you can count how many calls also there. So multiple paths can exist there, because I can call you maybe at 12 and then at 12:30 and then at 1. So multiple paths can exist here. I cannot call to myself, so that loop is not reasonable here. And this graph is just the same graph, but we don't have the direction here. And if you will remove the direction, then you will lose a lot of information also. Then you will not know that which number is calling to which number, but you at least know that this is the connection. 5 times there was a connection between this number and that number. This is the only information. So this is also a graph model which you can draw. And similarly, this one, example 11. This is a graph about different species existing in our ecosystem, mostly like squirrel, like mouse, these kind of species. The crow is also there anyhow. These are 2 birds. But mostly things, raccoon. This owl is also a bird, hawk is also a bird. So raccoon, squirrel, opossum, mouse, shrew, these are the similar kinds of things. So this is just a graph that how the resources which are available in this nature, how those resources are common between any of these 2 species. For example, raccoon and hawk, if there is an edge between them, then it means that they are competing with each other about the resources which are available in our world or nature, you can say. In ecosystem, actually, the proper word is. Hawk and owl is also competing for the resources. And similarly, opossum and squirrel is also competing. So this squirrel is competing with 1, 2, 3, 4. 4 different species, the maximum one. But this one has 1, 2, 3. Hawk is competing with 3 species. Similarly, shrew is competing with 1 and 2, and this one, 3 species. So this is just a graph. Also model, you can see example 7 to 10 and then 12 to 14, like that in the book with the illustration there. And this is the end of the section 10.1. Just a minute, I will. So now this is section 10.2, again about different terms, and we will see again some special types of graphs. So if there are the terms or the terminology, so then we will see different definitions. So sometimes we can say that one vertex is adjacent to another vertex. So if there is a word adjacent, then it means that they are neighbor. For example, I can say that one vertex U is adjacent to V in a graph G. I can say this. And if you have that term adjacent, then it means that they are neighbors. They are connected with each other through some edge, So they are, then U and V would be the endpoints of some edge. In graph G, you can also say that adjacency means what? Adjacency or adjacent means what? That U and V would be the endpoints of some edge. And you can also say the same thing with respect to edge. If you are focusing on edge and then you are saying that edge is connected with the vertices U and V, then you can also use this word incident. You will see this word also there in the textbook, so you don't have to worry. What it is, what is the meaning? If there is an edge like that, and you have these two edges, I'm just giving you the small example. So then what? If this is the edge E, if this is the edge E, you can call it, so edge E is called incident with the vertex U and V. If this is U and if it is V, you can call that this edge is incident, which means connected with the vertices U and V. You can also say like that. So when you have this word, so you don't have to worry. You have to take it as connection. So you can also say simply E is said to connect U and V or connect with U and V, whatever it is. So these are the different words. So you don't have to worry. It has the same meaning. So if adjacency is there, then we can say something about neighborhood of a vertex. I can introduce another vertex here, and then I can draw the edges here. So now, what are the neighbors of this node? If I will say it W, what are the neighbors of this node? V and W. What are the neighbors of this V? U and W. So now you are going to see something like that in definition 2 about neighborhood. So if we have a graph G is equal to set of vertices and set of edges, then we can represent the set of all neighbors for some vertex of that graph, for any vertex. And this small v is an element of this set of vertices, okay? So if you have the graph G, and that graph G will have many vertices, and if you want to find the neighborhood of one or two or maybe any vertex of that graph, and if you are calling that vertex V, then you can represent that neighborhood with this symbol, n of V. So this n is for neighborhood and this V is any vertex in the graph. And you can call it, or you can say this thing as a neighborhood of V. So as I told you, what is the neighborhood of U? This V and W. What is the neighborhood of V? This U and W. What is the neighborhood of this W? This U and V. This is simple. But next, in the next sentences, we are going to say something different, something large. So if you have this A, which is a subset of V, V is a set of vertices. For example, there are 10 vertices in the graph. So that V will have 10 vertices, 10 nodes. And let's A is a subset of V. Let's A is containing only 3 vertices, which is also existing in this V. So then you can say A is a subset of V. Okay? And now we denote by neighbor. Now you have to find the neighborhood of A. Okay? Neighborhood of A. Neighborhood of that subset A, okay? Not V. Not capital V, not only one vertex, which we talked here. No. Neighborhood of A. So that neighborhood would be like that. That neighborhood of A would be equal to union. You have to take union of, and these small v belongs to, you have to take one vertex from A first, and then second vertex from A, then third vertex from A, up to the last vertex available in the subset A. And then you have to find the neighborhood of each vertex which is available in that A. Each vertex. For example, in this subset A, I told you that if three vertices are available, then you will take V1 first, and then you will find the neighborhood of that V1. Union, okay, you will write it in curly brackets, and then you will take V2, you will find the neighborhood of that V2. So V1 union V2 union neighborhood of V3. So that is something going on here. That is something going on here to find the neighborhood of A. Now you will understand this sentence. We can represent N of A, the set of all vertices in G that are adjacent to at least one vertex in A. The set of, what is this N of A? The set of all vertices in G, in graph, all vertices. So that 3 and excluding that 3, the all other vertices. The remaining 7 you can say, because that 3 has the connection with those remaining 7. So set of all vertices in the graph that are adjacent to at least one vertex in A. In A, we have 3 vertices. The other remaining vertices will have the connection with at least one. More is possible, but at least one. If you are not understanding, you can just take this mathematical notation. It will give you this idea clearly. You have to take V1, V2, V3, which is available in A one by one, and you have to find their neighborhood, and then you have to take their unions, nothing else. When you are taking unions, then it means that it is possible that you will find, for example, V4, V5, V6 as a neighborhood of V1. And for V2, you will find V4, V7, V8. V4 is repeating. So if you are taking union, you will ignore the repetition of V4, nothing else. So you will ignore the repetition, and you will keep the vertices only for one time in the final set, in the neighborhood of A, in the final neighborhood of A. Definition 3, what is degree? In a graph, for example here, if you are, by the way, there are 2 categories of degrees. One is out degree, other is in degree. These are the 2 categories of degree. But we are just starting with the degree. So what is degree? Degree is the total number of edges going out from some vertex or going into that vertex. For example, if I can make another edge here. I am talking about this vertex, okay? I can talk at any, but I am just taking this as an example. What is degree? Degree is the total number of edges going out from this vertex or going into that vertex, okay? Or going into that vertex. Here we don't have the direction, so that's why maybe you will not understand. Maybe if you have the direction like that. So what is degree? Going out. This is going out. This is 1. This loop is also first going out and then coming into it. So 1 plus 2, so that is 2, and going out and coming into, this is coming into, this is going out 1, 2 and 3 and coming into 1 and 2, the loop itself. So 3 plus 2, 5. So the degree of this node is 5. But what is the definition of the degree? Degree is the total number of edges going out and coming into some node. And then look at it here, what he will write it here. Let's see. So degree of a vertex first for undirected graph. This is what I give you the idea with directed graph, okay? Before that, I told you maybe you will not understand going out and coming into. So that's why I draw these directions. So now here, degree of a vertex. So degree is, you have to tell the degree of a node, of a vertex. Degree is connected with the vertex. The definition of degree is connected with the vertex. So degree of a vertex in an undirected graph is the total number of edges connected with it. Undirected graph, so that's why connected with it. When you don't have the direction, so then you can say incident with it, connected with it, that's okay. Because you don't have the direction. You don't have to focus on going out and coming into. But if it is a directed graph, then you have to focus on how much is going out, how much is coming into, or like that. So for an undirected graph, total number of edges incident with it, which means connected with it, it means vertex. Except that a loop. Because loop, if you have a loop on a vertex, then it will be counted twice to the total number of degree. And you can represent the degree with this dig into V for undirected graph. Keep this thing in your mind. For undirected graph. If it is directed, you can also represent it with dig into V, but then you have to count the outer degree and in degree, and then you have to sum it up. That would become the dig into V. For example, what are the degrees and what are the neighborhoods of the vertices in the graph G and H here? This is G, this is H. You have to give the number of degrees of each vertex of each vertex. You have to count the number of degrees, and then you have to give the neighborhood also. This is easy. So this is undirected graph. There is no direction here. First, you have to focus also the direction is there or not. So there is no direction, undirected graph. So for what is the degree? 1, 2, total number of undirected, just count the edges. So degree of A is 2. Degree of B is 1, 2, 3, 4. 4. Degree of 3 is 1, 2, 3, 4. The degree of C is 4. Similarly, degree of F is 1, 2, 3, 4. E is 1, 2, 3. Degree of G is what? 0. Degree of G is what? 0. Degree of D is what? 1. So you have to write the degrees of each thing. Degree of A is 2. Degree of B, C, F is 4. All these are 4. Similarly, degree of G is 0. And what is the neighborhood? Neighborhood of A is B and F. Neighborhood of E is what? This F, this B, this C. So B, C, F. Okay. Neighborhood of A is what? BF. Neighborhood of this B is what? 1, 2, 3, 4. So A, C, E, F. Okay. Just ordering. If you will not order, if you will write A, F, C, E, that's okay. No issue. So this is the neighborhood. And neighborhood of G is what? Null. Similarly, you have to do for this one. But here you have the loop. So loop will be counted twice. For example, degree of B is what? 1, 2, 3, 4 plus 2, 6. Degree of B is what? Maybe you will, degree of B is 6. And similarly, the neighborhood, it's easy. The vertex of degree 0, if any vertex have the degree 0, that vertex would be called isolated. This is now the terminology. This vertex G, which does not have any degree, so that vertex would be called isolated. Yes.
Neighbor of the B is supposed to be definition.
The neighbor of B.
So, the loop
So what you are going to say here?
is starting the loop also if I'm my neighbor.
Yeah, you have to count. Maybe let's see. Neighbor of B, okay? A, B, C, D, E. Yes. Due to that loop, we are counting it.
Does it make sense? As you said in previous.
Yeah. But these are not those graphs, okay? These are general graphs with A, B, C, not with the names of the friends. Okay? Not with, this is not friendship or acquaintanceship. That was real example, but this is some representation, example of just representation. If that would be like that, then maybe we will not. We will not consider. So if some vertex has degree 0, then that vertex would be isolated. You can call that vertex isolated. And there is another term called pendant. If you have a necklace around the neck and then the last bead that you have just there, for example, if you have the necklace, the last bead here, if you have something here, so that would be called pendant. So what is pendant? Which has a degree 1. For example, this D, it is just hanging down in a hanging position, okay, like a pendulum. So the vertex which will have the degree 1, so that would be called pendant. So now there is an example, and in this example we have a question that what does the degree of a vertex in a Naiche overlap graph? And that graph is example 11. Previously, in previous section, section 10.1, we have seen example 11 of hawk and squirrel and species. There was a graph about species. So that was example 11. So what does the degree of vertex in that graph? So it is, the question is not asking, give me the degree of each vertex. No. What is the meaning of the degree there? This is the question. What is the meaning of the different degrees there? Okay, the question is, what does the degree of a vertex in that graph? It is, the question is not what is the degree, what does. Degree is doing what in that graph? Degree is doing what in that graph? So asking about some conceptual thing. And then, so what does the degree of vertex in that graph represent? Represent what the degree there in that graph have, what kind of representation? And then the another part of the question is which vertices in this graph are pendant? So is there any pendant there or isolated vertex there? If there are, you have to just give the name of that vertex. So if you will go there, so this is 1. So here we have the degree 3, 3, 3, 3. You just have to look over. So this squirrel has degree 4. So mouse is pendant. Oh? This is what we know. And okay, you can talk that here, degree, for example, degree is representing You have to identify the relationship. So you can, what is the concept? Degree is representing the competition of resources between different species. So, for example, here raccoon is competing with owl, hawk, and squirrel for the resources which are available in the ecosystem. And here, the degree of the squirrel is representing that squirrel is competing with 4 other species about the resources which are available in the ecosystem. And squirrel is competing with opossum, raccoon, crow, and woodpecker. So this is what degree is representing. This is the answer of the first part. And we have only mouse is a pendant, and we don't have any isolated vertex in it. So now this concludes the answer of that question, which you can read it here. Degree is representing what? Number of species competing against each other for resources in the ecosystem. And for example, squirrel, the degree has 4, competes with 4 other species. It is mentioned here. Mouse is pendant because mouse competing only with shrew with 1, degree 1. And there is no isolated species or isolated vertex in that graph. So now we have the definition of some theorem here. If we have a graph G which have the set of vertices and the set of edges, and if it is undirected, then this is true for that graph. Then this is true for that graph. What is this thing? This means that you can double the number of edges. M is what? M is the number of edges. You can double the number of edges, and then it would be equal to the sum of all the degrees of the vertices. What it means, what this equation is giving you the meaning. If you have the undirected graph with set of vertices and set of edges, then this is true for that undirected graph. This is true for all undirected graph, okay? What this equation is saying, that if you have m edges in that graph, then what you will have, you can double the number of edges. That would be equal to total number of the degrees of all the vertices available in that graph.
The degree of G.
Which,
The degree of G.
the degree of whole G. Yeah. So it means that you have to, you can say this small v belongs to set of vertices, capital V, which is this one. So you have to take vertex V1, V2 up to Vn, whatever it is available in that graph, and then you have to count their degrees, and then you have to sum it up. Due to this summation, you have to sum it up. Whatever the result would be, that would be equal to the double the size of the number of edges. And it is written that if you have multiple edges or loops in the graph, even then it is true. Even then this handshaking theorem is true. Now, for example, how many edges are there in a graph with 10 vertices of degree 6? There is a graph with 10 vertices. Now V is 10, each of degree 6, and each vertex has degree 6. How many edges are there? So you can use this formula here, this theorem here, to find, because m is the number of edges. You have the total number of degree. If you will have this equation 2m is equal to summation, you have the total number of vertices and each vertex has degree 6. So it means that 6 multiplied by 10, you have the 60 total number of degree. So this right hand side is now 60. So 2m is equal to 60 and m is what? 30. So in this way you can find the number of edges, nothing else. It is simple. Theorem 2. Again, if you have undirected graph, and if you have undirected graph, and that an undirected graph has even number of vertices of odd degree. This is saying that if you have undirected graph, that graph will surely have even number of vertices, but the condition is the degree would be odd. The degree would be odd. Okay, just keep this statement because maybe in future, in upcoming slide, we will use this statement somewhere. Okay. I will try to stop here at 12, not here at 11, okay? Now definition 4. Again, now these are again the same things, just maybe some things, some terms are repeated, some terms are new, nothing else. These are only terms. If you have a pair of vertices, if you have a pair of vertices starting from U, ending on V, so this is what? If you have something like that within the parenthesis, U comma V, that would normally represent an edge. That is a representation for an edge. So if you have an edge of the graph represented with U comma V within the parenthesis with directed edges. So now you have the directed edges. If you have the edge and the direction is also there, then you can call it U is said to be adjacent to V. So if this is an edge, again, I'm just drawing. If it is U and if it is V, if this is an edge, direction is given. So if this is an edge, UV in a graph with directed edges, okay, direction is given. You can call that this U is adjacent to V, okay? Or V is adjacent from U due to this direction. Due to this direction. So now you will have the things like that in the textbook, if you are reading the textbook. So then what? U, if it is written there, U is said to be adjacent to V, then it means you are going from U to V. So your direction is from U to V. And how you will represent adjacency from V to U in opposite direction? V is adjacent from U. You can also call this initial vertex U as the initial vertex. If you have the pair like that, you can call this U initial vertex. And you can call this V the terminal vertex or the end vertex, where the edge is ending, where the edge is terminating. These are the different words you will find in the chapter. So that's why these are the different definitions first and then the things after. And if you have the loop in that directed graph, then you can understand that the initial vertex and the terminal vertex of the loop would be same. If you have the loop here, then it is from how you can represent this edge V comma V. So the initial vertex and the end vertex is same. So it is V. So now V comma V is what? V is adjacent to V. V is adjacent from V. Both are there. So anyhow, definition 5. What is in degree? So I don't know either you are looking at this. Okay. So for example, if this is the node, any edge coming into it any edge coming into it would be counted as an in degree of that vertex. And you have to look, for example, if I say, what is the in degree of this vertex V? You have to count what are the edges coming into that vertex. What are the edges coming into that? So this is the 1 and this is 2. So 2 is the in degree of this node. And if I say, and you can represent it with dig minus V. And what is out degree?
So
The edges which are going out from that vertex. So what is the out degree of this vertex? There is no any edge going out. So 0. For example, here, what is the in degree of this node in this graph? So in degree 1, this is 2, which is coming here. This is coming into it, and no one else. So 1 and 2. Okay. So 2 is the in degree. Out degree is what? Going out, going out, going out. 3. And degree is what? 3 plus 2, 5. Okay. When you will count in degree and out degree, it will be 2. No. Okay. You have to count. 1, 2, 3, and 4. Loop would be counted. So 4 plus 2, then it is 6. Okay. So 1, 2, 3, and 4. 4 is the outer degree. 2 is the inner degree. And what is the degree? 4 plus 2. So I'm just so that you will not confuse. Degree is what? Out degree is what? In degree is what? Don't confuse. These are the easy things. This is not difficult. I think this chapter would be easy for you. But you have to focus on different definitions. And only then you can identify the correct things. Otherwise, you can mix these different definitions. You can mix the definition of in degree and out degree and degree. These are different things. Okay. Example 4, find the in degree and out degree of each vertex directed at shows in figure 2. So this figure is given to you. You have to find the in degree and out degree. That is easy. So for example, what is the in degree of this A? 1 and coming into it 2. So 2. Dig minus A is 2. What is the out degree? First focus on the in degree. Okay. What is the in degree of B? Coming into it. So 1, 2. This is going out. So 2. So in degree of dig minus B is 2. You can write like this. What is the here in degree? I have already considered this loop, so there's no need. You can do it by yourself. What is the outer degree of this? Outer degree, not in degree. So you have to focus on the out, the edges which are going out. This is 1. This is coming into, and this loop, okay? Going out. So 2. Outer degree of C is 2. So dig plus C. Dig plus C is 2. And in this way, you can go on and give the answer. Now we have another theorem. This is saying that if you have a graph G with set of vertices and set of edges, and if this graph is directed graph, if this graph has directed edges like that, then when you will count the in degree of that whole graph with all the vertices, that would be equal to the out degree of that whole graph. That would be equal to the total number of edges in that graph. This is the statement of the theorem, what it is saying. So dig minus V means what? This small v is belonging to capital V. Capital V is what? It is a set of vertices in that graph. So you have to take, you can just suppose that this is V1. So in degree of V1 plus due to that summation plus in degree of V2 plus in degree of V3 and so on plus in degree of Vn. So now you have summed up all the in degrees of that graph. That would be equal to out degree of that graph. So out degree of V1 plus out degree of V2 plus out degree of V3 and so on, out degree of Vn, what would be the result? That would be equal. Okay, that would be equal. And what would be their individual result? That would be equal to the total number of edges in that graph. This is what's saying. This is these pipelines is giving you the meaning, the cardinality, the size, total number of edges in that graph. So what is underlying undirected graph now? What is underlying undirected graph? Graph with no direction. So undirected graph, graph with no direction, that results from ignoring the direction of edges is called underlying undirected graph. For example, this one. If you will ignore the direction of this graph and if you will make a new graph without direction, so that graph would be called what? Underlying undirected graph. That would be called underlying undirected graph. The example is not given there, but I can give you a question. Draw an underlying undirected graph for this figure, just to tease you. But I'm not telling you, so now it's easy. If I will not tell you, then it will be what? Wallahi Ustad, hada sawal ajeeb, hada sawal mushkil, wala, wala, wala. You will say the things like that. So I can give you a question, I can give you this figure and this graph, and I can say, draw the underlying undirected graph for this figure. And then you have to do what? You have to only remove the direction. And the remaining graph, whatever it is, that would be called underlying undirected graph, nothing else. Okay. What is complete graph? I can also say draw a complete graph. So now you have to focus. I can also say draw a wheel. I can also say draw an NQ. So now you have to focus. What is complete graph? First the definition, and then we will see some examples. So a complete graph would be a graph on n vertices. N vertices means it can contain any number of vertices. N, you can give a value to the n, 1, 2, 3, 4, whatever it is, and then you can have some kind of a graph. But that graph would be called complete graph if that graph would be simple graph first. The first condition is it would be simple graph, which means it will not contain multiple paths and loops. Good. You have to keep this definition in your mind. Only then you will not do any mistake. So complete graph is what? You can represent that complete graph with Kn. K is just a variable, and then here n means for one vertex, for two vertex, for three vertex, having four vertex, or whatever it is, we will see. So a complete graph would be a graph. First, it would be a simple graph. And what is the meaning of simple graph? It means that graph will not contain loops. That graph will not contain multiple edges. Okay. And then it will contain exactly one edge between each pair of distant vertices. Exactly one edge between each pair of different. So for example, these are two different vertices. So this is a pair. So it will contain exactly one edge, which means no multiple paths, nothing else. Nothing else, which means I cannot draw an other edge here. Okay, that is not allowed. That is not allowed. How can I remove? Yeah. So then that would be called a complete graph. And the opposite of that one, if you have multiple parts or whatever the thing, if the condition is not fulfilled, then it would be called incomplete or non-complete. In the book, the word is non-complete, so I have taken, otherwise it is not a perfect word, okay, English-wise. It should be incomplete. But in the book, it was non-complete, so I cannot challenge the book because English is not our language. But one thing is sure that that book was not written by English speaker. Maybe the authors are from Europe, okay? Maybe Germany, France, or whatever. Anyhow, for example, these are the example. If n is 1, which is for the number of vertices, can we draw a complete graph? Yes, K1, only one node. And when n is 1, it means one node. So, okay, draw that one node and there is no any edge. Okay, that is a complete graph? Yes. It is a simple graph, no loop, no multiple paths. The condition is fulfilled. No loops, no multiple paths. Condition is fulfilled. Condition is fulfilled. Okay, now when you have n is equal to 2, so K2, it means now your graph contains two vertices. Okay, that these have the two vertices and only exactly one edge. No multiple path, only you can draw one edge. Draw that one edge. And now this is K2, okay? This is what? K2. And is it a complete graph? Yes. K3. When you have n is equal to 3, okay, this is now 3. Now draw exactly one edge between each different pair. Okay, this is pair, draw that one. This is pair, draw that one. This is different now. We are not, okay, this is different now. Exactly one edge. So this is K3 and it is a complete graph for K3. Similarly for K4. And these things, each exactly one edge between each pair of different, distinct, different vertices. When you have one vertex different, then you can draw that exactly one edge. Same is for K5, K6. So these are the examples of the complete graphs, which you have here on this diagram. Here, now some graphs are called cycles. Some graphs are called complete graphs. Some graphs are called cycles. And you can represent it with Cn, for example. You can represent with any variable, but here we have Cn. But for cycles, if it is a cycle, it should be like round, complete loop-like thing. And then what? It can start with n greater than or equal to 3. If it is less, if it is 2, 1, so this is not cycle, this is not cycle. Cycle is starting from here. Okay. So n greater than or equal to 3. This is the condition now. 3, 4, 5, whatever it is. But 2, 1, it is not cycle. So it will consist of n vertices. V1, V2, and so on. That would be, these are the vertices that would be in that graph. Edges would be from V1 to V2, and then from V2 to V3, and then from V3 to V4, and then from Vn minus 1 to Vn. Vn is the last one. But then again, another is needed from Vn to V1, which will complete the cycle. This last edge is important because it will complete the cycle. From last to the starting one. It is representing what? From the last node to the first node. And this completes the cycle. And we have different cycles for C3, C4, C5. It is mentioned here in this figure 5. See for C3, okay, when you have 3 vertices. So we will, if it is V1, start from V1 to V2, V2 to V3, V3 to V1. cycle complete. Start from V1 to V2, V2 to V3, V3 to V4, V4 to V1, cycle complete. That thing is not needed, okay? Which was here in the graph, complete graph. It is only cycle, outer boundary. Okay, this is for C5 and this is for C6. You can see by yourself. Now the wheels. Wheels have only some additional vertex inside the cycle, and then you have to connect all other vertices with that additional vertex, nothing else. We can represent that wheel with Wn. We can add additional vertex to a cycle, Cn, and here also for the wheels n greater than or equal to 3, that condition is same. And then you have to connect this new vertex to each of the n vertices which are available in the cycle. For example, here, if it is a cycle, if this one is a cycle C3, you have to introduce some node here, and then you have to connect all these nodes, all these nodes to this vertex. That will complete the wheel. That will complete the definition of wheel. This is W3. Similarly, you can do something for W4 and 5 and 6. I am stopping here and I will start from here. I can continue maybe one slide. Yeah. And then the next lecture would be shorter. I don't know. Let's have a look first and then I can decide. It would be shorter or not. Hmm. All. It was an advice sent to us by the dean that you have to cover all the COs. So now what I will do, maybe for CO1, CO2 and CO3, maybe I will keep the percentage of marks I will keep less or low in the final exam. But from CO4, chapter 4, 5, 6, or CO4, 5, 6, and 7, I will keep the ratio of the marks higher as compared to the CO1, 2, 3. This is what I can do. Sorry.